Let's try and answer a question now, in particular regarding the spring-pulley-mass system shown over here. You see the spring element, the pulley, and then there's a mass or possibly a weight hanging down here. The question is, what should the constraint relations be? In other words, going back to a chapter 2 concept when we talked about constrained motion, remember that we described there a procedure. And the procedure went something along the lines as follows. We need to establish an arbitrary datum, and then we need to identify all of the variable points by shooting coordinates off of that datum. And then we need to come up with the equation of the rope that we can then begin to analyze. So let me motivate this protocol on this particular problem that you see before you. Now I've drawn two pictures of this same system, one in its before state, one in its after state when it's displaced just an increment downward from where it began. And I'm trying to color code the before to after coordinates in blue and green ink respectively. So let's just focus on the before picture for a second. What could possibly be variable in this picture so that I can come up with a rope equation? Well, first of all, let's say this position of the spring right here where my mouse cursor is, that could possibly stretch, right? So that's a variable point. And then the other thing that can move is, let's say, this center point on the pulley. As this spring is getting stretched downward, this pulley is also going to be able to move downward. And so I can right away identify 2 points in this picture that are variable. The x sub s for the spring and the x sub p for the pulley. Now I want to come up with this segment of the rope. Let me do that in maybe a stark red color so that it stands out. I want to come up with this segment of the rope and this segment of the rope, and then that'll give me the equation of the rope. Now, someone may say, look, there is a segment of the rope down here slung underneath the pulley, and that is in the form of a semicircle, right? And if I just call this pulley as having a radial dimension r, then this segment of the rope underneath here, people would agree, is going to have a value of pi times r. But this is just a constant. And remember that we're not really interested in things that are constant. Okay? So let me just go ahead and get rid of anything that is constant. I'll just cross that part of it out. And let's come up with, in blue, let's come up with the equation that describes this segment of the rope and this segment of the rope. And to do that, I think you would agree it's going to be xp minus the xs, that's the right little segment. Then I have to add back in the left segment, which is xp, and all of that, let me just say, is going to be some length of rope. Let me call it capital L. And I can do the same procedure on the right for the green slightly displaced configuration. And when I do, I get an after rope equation. I get the before rope equation that I just showed you. And then when I take the difference, you'll notice that I'm going to get 2 times a delta xp minus a delta xs is equal to 0. It's 0 because we had established that whether I call that L for the length of rope or L prime, they're one and the same. So obviously L prime minus L would be the same thing as saying L minus L or L prime minus L prime. And so it's a 0. And what do I find out at the end of the day? I realize that the spring is going twice as much as the pulley, or put another way, the pulley is going only half as much as the spring. And that's this relationship. Now, let's also remember that once I get it in its incremental form, which is this equation, then I can go through and divide both sides by delta t, take the limits, and when I do that, I can get my velocity relationships. In other words, the spring speed is going to be equal to twice that of the pulley. And then when I take one more time derivative, I can switch from blue to green to indicate velocities being, being taken into accelerations, and the acceleration of the spring is twice that of the pulley. Now, one last thing I want to say before I leave this idea is, if I were to try to come at a more quick answer just visually, but if I were to do a by inspection type of approach, I hope you would agree that if I were to displace this pulley by some amount, let's say I displaced it down by some increment like this, for example, all right? So it went from here down to here, all right? And the spring went from here down to over here, let's say. All right, and I can put anything I want here. I can say, let's make this 10, let's make it 10 millimeters, all right? I just picked something. Then you would agree that the amount of rope that was needed to move the pulley from its original configuration to the one beneath it should be a length of rope of 5 millimeters on each end to give me back that 10 millimeters that it went down. And so what I've tried to show just through a by inspection approach is the same idea, that yes, just by looking at this, it does make sense that the spring is going at a rate of twice that of the pulley.